In this video, we're going to talk about 8.1 Objective 4, where we construct and interpret sampling distributions for the sample mean or proportion. Question 1 says, assume that cans of cola are filled such that the actual amounts have a population mean of 16.00 ounces. A random sample of 49 cans has a mean amount of 16.19 ounces. The distribution of sample means of size n equals 49 is normal with an assumed mean of 16.00 ounces, and those sample means have a standard deviation of 0.2 ounces. Complete parts A through C. So how many standard deviations is the sample mean away from the mean of the distribution of the sample means? So we're going to say 16.19 minus 16.00 divided by standard deviation 0.02 divided by the square root of n. This is our formula for z equals x bar minus mu over sigma divided by the square root of n. This, and sorry, we're not doing that yet. We are just doing x minus mu over sigma. We'll get to that other one with the central limit theorem in just a second. And this is 9.5 standard deviations away from the mean. In general, was the probability that a random sample of size 49 has a mean of at least 16.19 ounces. I'm going to use my calculator for this. Second distribution, normal CDF, at least 16.19. And I need to stick in a big number like that represents positive infinity. My mean here was 16.00. My standard deviation was 0.02. And I come up with a very small number that's basically 0, because that is a 0 with 20 zeros in front of that 1. It's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then that 1, 0, 6, 7, 4, 7, 4, 6, 7, 8, 4. That's what that number is. It was written in scientific notation. It's basically 0. Does it appear that consumers who purchase cans from this particular sample were being cheated? Why or why not? It does not appear that the consumers are being cheated, since the probability from part B is so small. It appears most likely that the actual population mean is greater than 16.00 0.00 ounces. Therefore, the probability that consumers were getting cans of cola that were filled such that the actual amounts were less than 16 ounces is very small. Okay. Let's move on to problem 2. A population consists of a batch of 24,673 aspirin tablets and includes 1,104 that were defective because they did not meet specifications. So let's find that. 1,104 divided by 24,673 gives us a population proportion P of 0.045 when we go to the nearest thousandth or the nearest tenth of a percent. Now, and this was P equals 1,104 over 24,673. Our P hat is going to be 17 over 225. So 17 over 225 is equal to 0.076. Now let's look at part C. How does the discrepancy between the population proportion and the sample proportion, how can it be explained? Random samples collected with sound sampling methods may vary, and the sample proportions differ from the population proportion because of sampling error. That's one of the options here. It could be that this was a bad batch that we took samples from. That's one of the things that we're going to be interested in trying to figure out is sampling like this for quality assurance and quality control. But this could just be due to randomness. We can't say for sure right now until we learn some techniques later on how we would test for that. A quarterback threw 5 interceptions in his first game, 6 interceptions in his second game, and 4 interceptions in his third game, and then he retired. Consider the values 5, 6, and 4 to be a population. Assume that the samples of size 2 are randomly selected with replacement from the population. Complete parts A through C below. List the 9 different possible samples and find the mean of each sample. So we could have 5, 5. We could have 6, 6. We could have 4, 4. We could have 5, 6. We could have 5, 4, like that. We could have 6, 5. We could have 6, 4. We could have 4, 6, and we could have 4, 5 needs to be around here somewhere. There it is. So let's make sure that I got all of them. A, G, H, O, P, S, T, X, and that bracket symbol there after the letter Z. That's everything. Okay. List the mean of each of the samples. If multiple samples have the same mean, list the same mean multiple times. So I'm just going to make a don't use the set bracket here. So the mean of 5 and 5 is 5. The mean of 5 and 6 is 5.5. Let me go in order here. The mean of 4 and 5 is 4.5. The mean of 4 and 6 is 5. Mean of 6 and 5 is 5.5. 6 and 4 is 5. 6 and 6 is 6. 4 and 4 is 4. 5 and 4 is 4.5. So 5.0, 5.5, 4.5, 5.0, 5.5, 5.0, 6.0, 4.0, 4.5. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 6, 7, 8, 9. All right. What is the mean of the sample means? So 5.0, 5.5, 4.5, 5.0, 5.5, 5.0, 6.0, 4.0, 4.5, 2, 3, 4. That's 20, 7, 12, 16, 21, 26, 31, 37, 41, 45. 45.0 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9 is 5.0. Then is the mean of the sampling distribution from part B equal to the mean of the population of the 3 listed values? So let's check that out. 564 divided by 3 is 15 divided by 3 is 5.0. So this 5.0 and this 5.0 are the same. So yes, they are. The mean of the sampling distribution from part B is equal to the mean of the population of the 3 listed values. And those means are always equal. That this is just a truism that the mean of the sample means is equal to the mean of the raw data. All right, let's look at the next problem. The ages and years of the 4 leaders of a certain country when they were assassinated in office are 63, 44, 45, and 64. Consider these 4 ages to be a population and complete parts A through C below. Assuming that 2 of the ages are randomly selected to form samples of size n equals 2 with replacement, find the mean of each of the 16 possible samples. So we're going to have 63, 63, 63, 44, 63, 45, 63, 64, 44, 63, 44, 44, 44, 45, 44, 64. And we have 45, 63, 45, 44, 45, 45, 45, 64, 64, 63, 64, 44, 64, 45, and 64, 64. Those are my 16 options. Then we're asked to find the mean of those two things. So let's go ahead and let's list all those options out here. I don't want to do all that by hand. So we've got 63, 63, 44, 44, 44, 44, 45, 45, 45, 45, 64, 64, 64, 64. And then over here we have 63, 44, 45, 64, 63, 44, 45, 64, 63, 44, 45, 64, 63, 44, 45, and 64. And then this one is going to be the values from L1 plus L2 divided by 2. And then so let's list the means of all the samples here. Are 63, 53.5, 54, 63.5, 53.5, 44, 44.5, 54, 54, 44.5, 45, 54.5, 54.5, 63.5, 54, 54.5, 64. Should be my last one. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now I want to find the mean of all those things. So I'll let my calculator do that. Second list, mean of L3. It's going to add them all together and divide by the number of things in the list. So that mean is 54. And they're going to ask me, is that the same as 63 plus 44 plus 45 plus 64 divided by 4? And it is. So the mean of the sample means is equal to the mean of the population of the 4 ages. And this is always true, that those means are always equal. All right, that's it for this video. And we'll come back next time and we'll talk about 8.1 Objective 5. See you for the next video.